Okay, next talk is by Aparna talking about sparse linear regression and the lattice problems. Yeah, please.
Thank you. Hi, everyone. I'll be talking about joint work with Nikon Baffa and Vinod Vaikuntanathan on sparse linear regression and lattice problems. Let me give the setup for sparse linear regression. So you're given a matrix X and a vector Y, which is modeled as this matrix X times some secret vector theta star plus some small noise. You also know that theta star is actually k sparse, so it has at most k non-zero entries. So Y is close to a linear combination of at most like k columns of X, but you don't know which. And the goal is to recover theta star. So you want to find a k-sparse theta hat, like an estimate, that minimizes this prediction error, which is sort of the norm of the difference between what theta hat would predict versus what the true theta star would predict. For some context, this is a really important problem in statistics, and it's usually studied in the setting where X is a short and wide matrix. So if X is m by n, m is much less than n. And the sparsity of theta star is what allows the solution to be unique and meaningful. Okay, so in terms of algorithms, the naive algorithm you would first think of is to do a brute force search over all k subsets of the columns of X, and then do and solve the least squares problem. But for an m by n matrix, this would take time roughly n choose k, which is exponential in the sparsity parameter k. But this does achieve the information theoretically optimal prediction error, which is essentially the amount of noise that was already present in your input data. But the algorithm that people use in practice is called lasso. So how does it work? So remember, the goal is we want to minimize the difference between x theta and y, but subject to the constraint that the number of non-zero entries in theta is at most k. So its so-called L0 norm is at most k. Equivalently, you could write like a single objective function and optimize over all theta, as long as you add this extra term, which is the sparsity of theta multiplied by some appropriate factor gamma. But the problem with this is it's not convex. In fact, it's NP-hard to solve this optimization problem. So what people do in practice is relax the L0 norm to the L1 norm of theta. And this objective is now convex, so it can be solved efficiently. And miraculously, it actually works pretty well in practice, often. And the prediction error you can bound, but the problem is that the bound depends on how well conditioned your design matrix X is. So in particular, the bound is inversely proportional to the restricted eigenvalue constant of this matrix X, which is, and I'm going to gloss over a lot of details here, but you should think of it as like the minimum ratio between the norm of x theta versus the norm of theta for all sparse theta. For more intuition, think of it as the extent to which x can kill a sparse vector theta. So the really nice thing about lasso is that when you model the design matrix as having entries that are drawn independently at random from a standard Gaussian, which is a very reasonable model in statistics, and you have enough samples so that your solution is unique, the RE constant of this matrix is going to be really good, so lasso will achieve essentially the optimal prediction error. But for more general design matrices, it seems like there's a gap between what we can do information theoretically versus computationally with efficient algorithms. In other words, does SLR, or sparse linear regression, have a computational statistical gap? Or is there a better algorithm for SLR that does not have this RE dependence in its prediction error bound? So on the hardness front, Zhang, Wainwright, Jordan show that there is a fixed sequence of worst-case design matrices for which no algorithm can beat this RE error bound, as long as NP is not in P/poly. But on the algorithms front, the Kellner et al., this recent work by Kellner et al., showed that a preconditioned version of lasso actually manages to beat the RE prediction error bound for some class of matrices X, namely matrices with low tree width, and it's not important exactly what that means. So this shows that the story is slightly more nuanced, and it raises an interesting question, which is, how can we characterize the design matrices X for which SLR is hard? So in the set of all design matrices, we know that the ZWJ design matrix, it's hard to beat the RE bound for this. But we also know that there is a class of easy matrices for which preconditioned lasso beats the RE bound. So what's happening in the rest of the space? We make some partial progress towards understanding this. We show that there are more design matrices for which SLR is hard if you believe that certain lattice problems are hard. And we do this by showing a connection between sparse linear regression and bounded distance decoding. So what is this problem? It's parameterized, it's a lattice problem that's parameterized by alpha, a real number. And so you're given a lattice basis B and a target vector T, which is some lattice point shifted by a small error. And the goal is to find the nearest lattice point, BC star. You're promised that the error E is small. It's smaller than the shortest vector of the lattice by a factor of alpha. And so this is what ensures that the solution is going to be unique. An equivalent way of defining BDD that is more reminiscent of sparse linear regression is that you have a d by d square matrix and a target vector T, which is modeled as B times some integer vector plus a noise. And the goal is to recover Z under the constraint that Z is an integer vector. So in terms of algorithms for BDD, we have exponential algorithms that work all the way up to the parameter where alpha is just less than 1/2. But for more efficient algorithms, we believe this problem is actually hard. Because you could get a basis that is, you could get a lattice basis that is really bad. So in particular, the first thing you could think of doing is the Bayes rounding off algorithm, where you round B inverse T to the nearest integer vector. This is efficient, but the downside is that it works only if alpha is bounded by 1 over the condition number of the matrix, of the lattice basis. And this is like the ratio between the maximum singular value of B over the minimum singular value of B. One thing you could think of doing is first use LLL to improve the condition number of the matrix of the basis, and then do Bayes rounding algorithm. But this would work only for very small alpha. Okay, so to recap, SLR and BDD sound very similar. The difference is that with SLR, you're given X and Y, and you want to find a sparse solution theta hat. And with BDD, you want to find an integral vector Z. In both problems, information theoretically, the conditioning of the matrix X or B has no bearing on the problem. But computationally, the only efficient algorithms we know work well for only well-conditioned matrices. In the context of SLR, that's the restricted eigenvalue constant. And in the context of BDD, that's the condition number of the basis. So is there a more formal connection between SLR and BDD? And our main result is to show, yeah, there is a reduction between the two problems. So suppose you have a polynomial time algorithm that improves over lasso by some parameter beta. Then it gives you an algorithm for a binary variant of BDD, which beats Bayes' algorithm if the condition number is more than 1/2. Sorry, if beta is more than 1/2. Okay, so what do I mean by a beta improvement over lasso? What I mean by that is that the prediction error bound is going to be inversely proportional to the RE constant of x to the power 1 minus beta. And lasso was when beta is equal to 0. And another point, another explanation is needed here. So the binary BDD problem is not exactly BDD. It's like a variant of BDD we consider where we restrict the z star to be a plus minus 1 vector instead of any integer. And as far as we know, binary BDD's hardness profile is similar to that of BDD and was studied in this paper by Kirchner and Fook. Okay, so our main idea is to use a simple gadget matrix that transforms this sparsity constraint into an integrality constraint. So to understand, let's consider a toy example where we want to find a theta that is 1 sparse, so it has only one non-zero entry. If we add this additional row of like of the all ones vector and a corresponding one in the target vector, this linear constraint forces the single non-zero entry you have in theta to be close to an integer. Namely, it forces it to be 1. And this is sort of why we need to start from binary BDD as opposed to full-fledged BDD. And I want to note that a similar gadget appeared in this work by Harpal et al. Okay, so so how do the design matrices we end up with look like? They're composed of like 2 blocks. The first block is x1, which is where the rows are drawn IID Gaussian from this, with a covariance matrix that's closely related to the lattice basis. And the second block is this like fixed instance independent gadget matrix that doesn't worsen the RE constant of the matrix. Composing this theorem with worst case to average case reductions in the lattice world gives us a distribution over design matrices for which SLR is hard. And as far as we know, this is the first average case hardness result for SLR. But the caveat is that when we do this composition with the worst case to average case reductions, these design matrices have RE constant 0, so we don't really get like a tight, we don't get a lower bound that says the RE constant bound is tight. As our secondary result, we study the total regime where there are many sparse solutions. And we show that even if the top part of the matrix X1 is drawn from like a standard Gaussian, so it's really nicely structured, but since we're in like the total regime where there are many solutions, this problem is still hard if you believe the worst case hardness of lattice problems. And as a teaser, the proof goes through the continuous learning with errors problem, which was introduced by Bruna, Raghav-Song, and Tang a few years ago. So to summarize, in the unique solution regime, we have a statement that says a hardness of binary BDD implies hardness of SLR with Gaussian design matrices with covariance that's related to the lattice basis B. And this gives us the first average case hardness result for SLR. And our second theorem states that in the total regime where you have many solutions, it's hard to find even a single solution, assuming worst case lattice problems are hard. And I should repeat, all of these matrices are not exactly Gaussian. They have like a bottom block of matrix that's like a fixed gadget matrix to enforce this integrality constraint. Okay, so I'll conclude with 2 open problems. The first one is that this work by Kellner et al. Shows that preconditioned lasso beats the RE bound for some design matrices. And this is sort of reminiscent of basis reduction in the lattice world. So you can ask, can these preconditioning type techniques from one world improve algorithms in the other? And the second problem is we do show some average case hardness result for SLR, but it's still very much open if there's a natural average case distribution of design matrices for which the RE bound is tight for SLR. All right, thank you.
Any questions? Okay. Thanks again.